Okay, in today's lab we wanted to use a shear plate to test the focal length of a lens and a mirror. But before we get into that, I'd like to explain a little bit about the shear plate. The shear plate can be made two ways. It could be a plain parallel plate, or it could have a slight wedge angle. In this lab we used the shear plate with a slight wedge angle, and this is the basic way it works. If we have a wave front coming in, part of the wavefront is directly reflected up there, and then another part of the wavefront gets refracted and then reflected back up. And these two overlapping beams carry the same radius and are what you call laterally phase shifted. And it creates this interference pattern. This could be thought of as the Young's double slit experiment, where two wavefronts constructively and destructively interfere and create a fringe pattern on an image screen. These wavefronts create a virtual point source where the center of rotation is. And the shear distance is the area of overlap that the two beams are not interfering. And we have equations that can calculate that. We also have the fringe spacing and the divergence angle that we are going to record experimentally.
Alright, so I want to talk a little bit about the alignment for our system and how we performed our tests in this lab. So first we create a beam expander, the same way we did in the previous lab. We have our microscope objective, filter, and collimation lens. In this case we want our beam expander to fill the clear aperture of our shear plate. So we choose the microscope objective of about 0.4 numerical aperture, and our collimation lens of a focal length 250 millimeters to fill up that clear aperture. For our filter, we started off with a 15 micron filter. We were still having too much ringing coming out, so we stopped it down to a 5 micron filter to get rid of some of that extra ringing coming out of the filter. Now, like before, we used the shear plate to test the collimation coming out of our beam expander. And then for this lab, we can turn the shear plate around and use it to test different optical elements. So in this case, we have a flat mirror. The light will come through our system, come out collimated, pass through the shear plate, come off the flat mirror, and then back into the shear plate and create fringes. Next, we use the same type of technique to profile a lens. So in this case, we put the lens before the shear plate and again measure the fringe spaces, shear distance, and angle of the fringes. Our final setup was to measure the curvature, to profile a curved mirror. And to do that, we used a reference lens right after the shear plate, followed by the curved mirror. And the curved mirror will create fringes coming out of the shear plate at two locations, one at the focal point, and one where the radius of the wavefront coming into the curved mirror is the same as the radius of the mirror.
First, we tested a low-power mirror by placing it, as Matt previously mentioned. This is the fringe pattern that we obtained. We were able to measure the shear spacing, the fringe spacing, as well as our angle. These are our values. Using this equation, we can then solve for our wedge angle. We know our lambda, our alpha, and our index of refraction, and doing so gives us negative 0.0128 microradians. Finally, using this equation, which all of our variables are then known, we can calculate the radius of curvature of our wavefront. This turned out to be 124,000 millimeters. In this equation, multiplying it by 2, we can calculate the radius of curvature. But as we can see, our focal length is very large, and therefore our radius of curvature is also very large. We then tested a low power lens. We obtained a very similar fringe pattern as we did with the low power mirror. The only difference is our shear spacing was lower, as well as our fringe spacing. Using this equation again, we calculated a wedge angle of negative 0.078 microradians and a radius of curvature of our wavefront to be about 18,000 millimeters. Finally, we tested a short focal length mirror. We did it at two different locations to see where our fringes show the collimation. Taking the difference between these 2 points, we were able to calculate the radius of curvature of the mirror, which turned out to be 105 millimeters. And finally, with timesing that by 2, we were able to calculate a focal length of 210 millimeters. However, when we were testing to see when it was collimated, we weren't able to refer back to straight fringes due to the interference created by the wedge. We had to use these two spots that we obtained as a reference. As long as they were parallel to this line, we were then sure that our beam was collimated.